Welcome to Chapter 5 of 7D's Slurry Pump Expert course. In this chapter, we dive into the various styles of shaft seals used in slurry pumps, and share some of the non-confidential R&D learnings gained in partnership with Alcoa of Australia. To help improve the reliability of various style slurry pump shaft sealing devices, we share both conventional and unpublished R&D learnings in this training session. We review compression packing, developed over 5,000 years ago. Expellers, also known as dynamic seals, invented by Wilfley in 1919 before companies now claiming the concept even existed. Mechanical seals, followed soon after, in a 1923 patent. 100 years had passed with no significant changes. Approached by Alcoa to do a joint R&D project, trying to improve gland packing reliability, whilst reducing or eliminating water flush flows, we gained new industry learning. We share some of the new knowledge here. A special acknowledgement to Alcoa for sharing some of the R&D learnings, demonstrating their ECG commitments. 100 years on, the flush-free, leak-free, non-contacting sandgroper seal was born. The test rig, developed via collaboration with leading Alcoa engineers, enabled an enormous amount of data to be collected and analyzed. We believe it to be the most comprehensive build to date. During the past 3 years we have tested various gland packing, injectable packing, slurry lip seals, and mechanical seals. For those wanting a brief on the rig, press pause and refer right. Sealing where the pump shaft enters the wet end is a critical function. There are 3 types of conventional shaft seals supplied by nearly all slurry pump companies. Packed gland. These are addressed in Part A, this session. Expeller sealed. These are addressed in Part B. Mechanically sealed. These are addressed in Part C. A unique new style of seal, 7D's patent-pending, sandgroper, is addressed in Part D. This is a contactless, flush-free, leak-free seal that will run dry, work on suction lifts, runs cool, and absorbs virtually no power. During the past 30 years, 95% of clear liquid pumps have been converted from gland pack to mechanical seal. In contrast, the solids entrained in slurries make the use of mechanical seals more challenging, so they currently comprise about 10% of the market. Most remain gland packed. Most know intuitively that badly leaking shaft seals are a safety problem. Cause reduced bearing assembly life. Result in product dilution and loss. The cost to supply flush water is often overlooked. It typically needs to be treated and pressurized to 1 bar above the pump's discharge pressure. Be neutral, with pH between 6 to 8. Less than 30 micron solids size totaling less than 1,000 parts per million in volume. This is very clean water, often costly to attain, if even possible, on remote sites. Studies on large sites in remote areas have shown the cost to feed pumps with clean gland water is over $1.5 million per annum. That expense comes directly off the profit the processing plant would otherwise make. Let's review these costs in relation to the most common and oldest style configuration, a packed gland. Let's look at the cost breakdown. Dr. Ridgway's PhD thesis on slurry pump shaft sealware analyzed 220 slurry pumps at BHP's Olympic Dam operation in South Australia. The site uses flushed mechanical seals, but most remain gland-packed. The sleeves used on this site are extremely expensive. They use SAF 2507, super duplex stainless steel, laser-coated with tungsten carbide. They are around 8 times the price of conventional sleeves. Although high-end, they still consume around 14 per month. Even so, the gland water cost was still twice that of the sleeves. In 2023 terms, with increased energy and inflation, the cost ton for shaft sealing is 25 cents, resulting in around a $2,282,000 expense for the 9 megatons per annum produced at Olympic Dam operations. By the end of this chapter, you will be able to reduce shaft flush water, even do away with it, whilst improving reliability. It is possible to stop shaft seal flush across an entire operation, but to do so, knowledge is needed. With the knowledge gained in this training, you will be able to dramatically reduce the gland water flush flows whilst at the same time improving reliability. You will be able to analyze the best outcome for your site. For some it will be to upgrade their existing stuffing box arrangements, for others to install expellers, others will consider installing mechanical seals, and some may want to use our sandgroper seals. Many will use a combination of the 4 types, optimizing the selection for each individual pump. We will run through packed gland stuffing boxes first, then discuss expellers, then the various styles of cartridge mechanical seals used in slurry applications, and finally the sandgroper seal. By then you will be an expert on slurry pump shaft seals. Slurry pump shaft sealing, Part A: the packed gland stuffing box. Let's first look at how a packed gland works in clean liquid pump. Centrifugal pumps were initially sealed with greased hemp. I guess they loved burning that packing. This advanced into braided packing, better for reliability and safety on site. Packing is compressed against the shaft sleeve by a gland follower. With a flooded suction, that is positive liquid level above the pump suction nozzle, there is no need for a lantern ring. In a clean liquid pump, it could be replaced by another ring of packing. In nearly all applications, the stuffing box has a positive gauge pressure. In horizontal back pull-out pumps, the stuffing box pressure is typically around 30% of discharge pressure via the use of balance holes or pump-out vanes. These pressure-reducing impeller features also reduce the axial hydraulic thrust, taking load off the bearings. The function of the lantern ring in a clean liquid back pull-out pump is to prevent air being pulled into the pump, such as on a high suction lift, or flashing on a hot liquid application, as in a boiler feed application. In these cases, a flush from the pump discharge is directed to the lantern ring. On horizontal split case pumps, whose seals see suction pressure, flush piping from the discharge is common, to ensure the packing is sufficiently cooled. Because the packing is compressed against the rotating shaft, heat is generated. It is thereby essential that a small quantity of water flows between the packing and sleeve for cooling. Some suppliers say the flush flow should be 1 drop per 15 seconds. The industry body says that the flow should be 1 drop per 15 seconds for each 25 mm shaft diameter. Research and development test work proved this completely wrong. We will explain our findings during this session. Packing suppliers also recommend tamping the first rings during installation, so load is transmitted to the rings beside the gland follower. During research and development testing, we also found this was a waste of effort. Again, we will explain why during this session. Because gland packing will abrade the rotating shaft, a sacrificial sleeve must always used. In clean liquid pumps, 70% of the shaft sleeve wear occurs next to the packing gland. Research and development work showed this was not due to the amount of tamping, explained soon. Detailed instructions for installing packing are available for download with this training pack. Many key new learnings remain confidential within Alcoa and 7D. Sharing the following detail will help the industry be more efficient, sustainable, and safer. We confirmed an elastohydrodynamic lubrication film forms under the packing closest to the liquid pressure. As the liquid pressure increases, the lubrication film extends further towards the gland follower. Due to the lubrication film, even tamped after bedding in, the impeller side packing does not touch the sleeve. It is not performing an effective function. As the gland follower is tightened, it generates a force that compresses the packing rings in close proximity to the follower. Even when the inside rings are tamped, as the pump pressure increases, the film moves under the packing rings closest to the impeller. In high-pressure duties, the force applied by the gland follower against the rings closest to the follower causes severe compression in this area without sufficient compression force being transmitted to the inner rings of packing. The result is the external rings are doing nearly all the work. Their severe compression generates high torque, heat generation, the product flashes, then the packing burns. The packing generates torque, consuming power, with its magnitude depending on a friction factor, packing to sleeve, the shaft velocity, and the pressure sealed. The higher the velocity, pressure, and friction factor, the higher the consumed power. The power consumed generates heat. For reliable operation, the heat must be dumped. To prevent the packing burning, the heat must be dissipated. We found this occurs via 3 separable parameters. Gland leakage. Heat soak via the sleeve transferring heat to the pumped fluid and radiation to atmosphere beyond the gland follower. Where the packing material is not an insulator, insulators include PTFE and aramid, additional radiation via the stuffing box. When the heat is not removed, the liquid vaporizes under the packing. The rapid expansion of the steam then causes an instantaneous exponential load as it compresses the packing against the gland follower. The outcome is like someone instantly over-tightening the follower, generating more load and thereby more heat. After steaming up, the pump should be stopped, the gland follower backed off, time provided for the sleeve to cool, then start over. The higher the pressure and shaft speed, the greater the heat that needs to be dissipated. Accordingly, low-pressure pumps do not need much leakage. High-pressure pumps do. To select the optimum or even just suitable packing, pressure velocity selection charts and friction factors are absolutely essential. Otherwise, selection is guesswork. Where are these charts? They are not in supplier brochures. Where is the friction factor information for various packing materials operating against different sleeve materials with varying surface finishes? We asked the leading packing manufacturers for this detail. We were told tests to determine these parameters, critical to determining packing suitability, have never been done. The lead global engineer from one firm was honest and said rule of thumb information is used in the brochures, that is based on field experience across the decades. We determined published pressure ratings are based on valve stems, whilst the maximum sleeve velocity is based on rotating shafts. The brochures do not explain that the two interact and the maximum published pressure and velocity cannot occur together. Collaborating with Alcoa, 7D have conducted tests to determine the PV of two-fold packing, our grade of aramid, with our grade of graphited EPTFE. We have also estimated friction factors of the various packing grades on our mirror surface finish Wolfram shaft sleeves. We have discussed the liquid pressure in clear liquid pumps creating a slight flow between the packing and shaft sleeve. Now we introduce solids into the equation. We end up with two-body mode abrasion moving to three-body in most duties. The hardness of common ores in comparison to the shaft sleeve material often surprises even the most experienced people. See chart at right. If these minerals become embedded in the packing, they create a grinding paste that destroys both the sleeve and the gland packing. Even a mildly abrasive rutile will rapidly destroy soft shaft sleeves as ductile iron or 316SS. For the best reliability, it is essential to prevent solids entering the stuffing box. We first consider the most common type of slurry pump water injection, the full flow arrangement. In slurry pumps, a device called a lantern restrictor is fitted to the bottom of the stuffing box, the impeller side. It provides the function of a lantern ring, enabling cooling water to enter the packing area, but also has a built-in restrictor to throttle, restrict the water flush flow. The result being a water pressure barrier forms between the gland packing and the slurry. The longer the length of the restrictor, or the tighter its clearance, the higher the pressure barrier for a given flush flow. The lantern restrictor is fed with clean water at about 1 bar above the pump's discharge pressure. This creates a water pressure barrier in the lantern restrictor, preventing solids entering the packing. The flush flow injected is to create a pressure barrier, with nearly all the flow being lost into the slurry, rather than being used for cooling the packing. When used, pump-out vanes on the rear of the impeller reduce the seal chamber pressure to around 30% of the pump's differential pressure. The seal chamber pressure being the suction pressure plus the pump differential pressure. The restrictor throttles the excess flush flow to create a water pressure barrier between the packing and slurry. To reduce wear rates, balance holes are not used on slurry pump impellers. When back vanes are removed, such as on some manufacturers' high-efficiency impellers, the seal chamber pressure is close to the full pump discharge pressure. There are no vanes that reduce the seal chamber pressure, whilst also removing axial hydraulic thrust. The result is more work being done by the packing and thrust bearing. As full flow, metal lantern restrictors locate in the bore of the stuffing box. Generous clearances between the lantern restrictor and sleeve are supplied by OEMs. This ensures restrictors don't touch the rotating sleeve. Flush flows to attain the desired buffer pressure are very significant. More than 6,000 liters per hour is typical in mill duties. More than 99% of the flow enters the slurry with less than 1% entering the packing. Next we consider the low flow arrangement, which was developed in recent times to reduce the flush flow consumption of full flow lantern restrictors. For lighter duty slurry applications, away from mill and tailings, a plastic lantern restrictor is often used in modern slurry pumps. A bearing grade plastic, typically Riton, is used with tight clearances between it and the shaft sleeve. This enables the same throttling pressure in the lantern restrictor with a reduced flush flow. The bearing grade plastic locates against the sleeve, instead of the stuffing box bore. This enables a very tight clearance to be used. It beds in during initial startup. Due to tighter clearances, flush flows are typically 30% that of the full flow arrangement, whilst attaining the same pressure buffer between the slurry and the packing. The problem of course is soft bearing grade plastics rapidly erode. As the clearances open, the throttling effect reduces, the pressure barrier is lost, then increased flush flows occur. To maintain the tight clearance, hence low flush flow, these plastic devices should be replaced on a frequent basis. Now we review the ultra-low flush flow arrangement. A style avoided whenever possible. If the slurry pump has a very high vacuum on its suction, for example the pump is on a significant suction lift, it is important to keep air from being pulled through the stuffing box and into the pump. This is particularly true when the pump is off. In these circumstances, there is little resort but to set up slurry pumps like water pumps, using a lantern ring, neck ring, and a ring of packing in between. The problem of course is the ring of packing between the lantern ring and the neck ring gets slurry embedded under it. Ongoing maintenance problems are often the result. If you must pack a pump in this configuration, ensure you have an extremely hard shaft sleeve. In this configuration, flush flows are generally 10% of full flush arrangements. You will have a very low flush rate, but on severe slurries, especially with higher pressures, will have a high wear rate on the sleeve and packing. We now consider where ring mains versus standalone gland water supply pump sets will be needed. On many sites, general service slurry pumps are fed from the plant's process water system. These ring mains will usually have plenty of water available at a constant pressure. We now understand how the clearances between the lantern restrictor and shaft sleeve, plus the throttling length, govern the flush flow rate through the slurry pump. The lantern restrictor will throttle the flow so the desired barrier pressure keeps the slurry out of the packing. General service ring mains will only be suitable to feed pumps where the ring main pressure is at least 1 bar above the pump discharge pressure. For high-pressure pumps, such as tailings or autoclave feed, it is unlikely the ring main pressure will be sufficient enough to create a water barrier in the lantern restrictor. Separate gland water supply pumps will usually be needed. When separate gland water supply pumps are needed, how do we select them? If you were trying to maintain a constant flow, which would be intuitive after reading pump manuals nominating exact flow rates, a positive displacement pump would seem best for gland water. Not so. We are trying to keep a constant barrier pressure in the lantern restrictor. To do this, the flush flow will increase and decrease depending on the clearance between the restrictor and sleeve. The required flow varies. The flush flow in the manuals of OEMs is a general guide, giving you an indication of the flow to attain the buffer pressure and allows for some wear in the operating clearance. We therefore recommend variable speed-driven centrifugal multi-stage pumps be used on gland water supply. They should be controlled to maintain a constant pressure, not a constant flow. The gland water pump speed will increase or decrease to provide the flow needed to create the desired barrier pressure in the lantern restrictor. Now let us consider the benefit of using flow-limiting valves at the entry to the pump stuffing box. If just one pump in a ring main system has a gland seal fail catastrophically, it can consume far more flush water than was accommodated in the system design. When the gland water feed can't keep up with sufficient flow to maintain the ring main pressure, then the feed water pressure will drop. All other slurry pumps in the same gland water system then risk losing their lantern restrictor barrier fluid and every gland fails. This can be a very expensive failure. A very simple low-cost valve solves this problem. We recommend a flow-limiting valve size to allow about 20% more flow than estimated for the pump's flush water. We recommend a flow-limiting valve size to allow about 20% more flow than estimated for the pump's flush water. The lantern restrictor will control the flow to less than the flow-limiting valve will allow. We now look at fundamental variants that affect reliability. In his PhD thesis, Ridgway identified many factors impacted sleeve wear including the pump pressure, and thereby radial forces required on the seal. The hardness difference between the sleeve and ore. The particle properties, shape, size, quantity, volume. Contact length, sleeve OD, and sleeve velocity. During his time at Go Volumina, Bishop published an excellent paper addressing other impacts as shaft deflection that occurs on higher pressure units, and the impact of concentricity. These are critical considerations. If solids are kept out of the stuffing box, the solids have no impact. The packing load will be next to the gland follower, and this is where greater than 70% of the wear will occur. If solids enter the shaft seal, as Ridgway's research, then very substantial wear will occur under the packing ring directly beside the lantern restrictor, as fines will become embedded in this first ring of packing abrading the sleeve. So which styles of packing do we need to consider? If your gland water flushed stuffing boxes are keeping solids out of the packing, your packing is sealing against clean, pH-neutral, ambient, water. Unlike dry expeller sealed slurry pumps, discussed in Part B, you may not need aramid, Kevlar, slurry packing, which is often recommended by packing manufacturers as a high-grade solution to cope with abrasive particulate. Packing manufacturers often overlook highlighting the damage aramid does to sleeves less than 60 Rockwell C hardness, about 650 Brinell, or 700 Vickers. This is well beyond the hardness of standard shaft sleeves. For maximum reliability with low leakage, a high-quality packing is recommended. The packing needs to be selected to suit the sleeve velocity, gland operating pressure, temperature and pH. Don't be confused with all the variations. For low pressures, and clean flush water, low-cost high-strength glass fiber yarn impregnated with PTFE, and containing break-in sacrificial lubricant, can be cost-effective. Nearly all the flush flow is required to attain the barrier pressure. Typically 99% goes directly into the pump, through the lantern restrictor clearance and diluting the slurry. Only a tiny portion drips from the gland follower. A flow large enough to dissipate heat caused by friction passes between the sleeve and packing. Refer calculator in this pack for estimations of torque, power, flows. It is also common to have a flow passing on the outside diameter of the packing. This is particularly prevalent when the stuffing box is pitted from corrosion, or in poor condition. Sometimes the flow at the outside diameter of the packing can be as high as that on its internal diameter. Based on test laboratory results, we recommend a blend of graphite-filled EPTFE on one half, woven with aramid fiber, Kevlar style, the other. Arranged as shown, the black packing, the graphite-filled EPTFE, keeps friction low, with the graphite helping dissipate the heat through the stuffing box and sleeve. The yellow packing, the aramid fiber, resists abrasion, keeping particulate away from the softer packing. It also aids compression, so the gland load better transfers the compression loading further down the stuffing box. Let's consider the special bushings that are available. If you have poor quality gland water, with fines content exceeding 1000 parts per million, special bushes are available that clean the flush water, combined with tolerances that throttle the flush water flow rate. These bushes direct fines in the flush water into the slurry and clean water to the packing. These bushes do not clean the slurry. Instead, they clean the flush water, doing a great job in keeping the solids in the flush water from the packing. Do not believe brochures or people claiming these devices clean slurry. They do not. If the gland water does contain fines beyond 1000 parts per million, or the flush is turned off when the pump contains slurry, aramid packing and a sleeve with a hardness greater than 60 Rockwell C, about 650 Brinell, is recommended. This is well beyond the most common sleeve material, hardened 420 stainless steel, coated by a common manufacturer as C21. Now let's consider shutdown, when the flush water is turned off. So what happens to all the aforementioned seal configurations when you turn off your flush flow whilst there's still slurry in the pump's wet end, whether it's operating or on standby? In an instant, a significant amount of solids becomes entrained in the packing. When you restart the pumps, even though you've turned your flush flow back on, the solids are now in the packing, abrading the sleeve and destroying the packing. It's such a waste to flush standby pumps, but the flush must be left on whenever there's slurry in the wet end. One solution is to use a cal seal arrangement, which incorporates a lip seal from the expeller arrangements. The drawback is you no longer have a restrictor, so the flush flow is unthrottled, and becomes enormous. Let's now look at some numbers, so we can then consider optimizing chamber arrangements. Let's consider some calculations to understand why the same pump can have an extremely reliable and low wear gland, whilst in another duty, the same arrangement will be a disaster. The pump with calculations on the left-hand and right-hand side are identical. They have different speeds and suction pressures. The higher speed pump is running with an impeller that has its back vanes removed. One of the leading manufacturers does this with their high-efficiency impellers, with few understanding the problems this creates in gland-packed pumps. We also use a different grade of packing. One has lower friction than the other, with both suitable for highly abrasive slurries. The pump on the left has a standard impeller, with pump-out vanes, in a typical duty. The seal chamber pressure is 165 kilopascals, with the packing absorbing only 246 watts, a few old-fashioned light globes. The low friction but highly abrasion-resistant packing helps. The flow to dissipate the heat generated is about 20 drops per second. A small stream from this 12 by 10 G frame pump. The pressure versus velocity is low, and the pump will be reliable with the gland arrangement. In contrast, this same pump operating in a series application will be a disaster from a reliability stance. The high-efficiency impeller, without rear back vanes, has a 2,975 kilopascals stuffing box pressure. It is absorbing 20 kilowatts of power, elevated because pure aramid packing is being used. The torque is 215 Newton-meters, akin to shoving on the brakes in a car doing 60 kilometers per hour, just inside it starting to skid. It is effectively like operating a car with the brakes permanently on. The brakes will burn out quickly, as will the packing. The pressure versus velocity is very high, more than 25 times higher than the service on the left-hand side. To reduce stuffing box wear, this unit needs a rethink. The duty is beyond the pressure-velocity capability of the packing. In contrast, the more common duty, using two-fold packing, is well within the capabilities of the gland packing. We need to find a solution to the high head service. Let's reconsider how the pump in series is set up. Various solutions could be used, including fitting a mechanical seal. To do so will be very expensive, and when mechanical seals fail, they do so catastrophically. We would suggest a different arrangement with gland packing. Use an impeller with back vanes, instead of an impeller without them. If your current supplier does not have high-efficiency impellers available with back vanes, speak to 7D or other leading manufacturers who will be able to assist. Install a grade of gland packing that has a low friction factor, high velocity pressure capabilities, and importantly, can cope with abrasive factors. Various leading packing manufacturers will have suitable packing. 7D's two-fold packing will be suitable. Critically, ensure the pump shaft sleeve has a very hard surface finish, and if coated, that it is at least 2 mm thick. If not, the aramid portion of the packing will damage the sleeve in relatively short time. The 20 kilowatts of heat to be removed when using standard aramid packing, and an impeller without back vanes, is going to be nearly impossible. The required packing leakage to dissipate the heat is nearly 300 liters every hour. This spray jet will damage the bearings. The friction, even with an exceptionally hard sleeve, will damage both the sleeve and gland packing. The duty will be a significant maintenance headache. Changing the impeller to one with rear vanes, still possible in a high-efficiency design, will reduce the stuffing box pressure to 2,293 kilopascals. Installing two-fold packing will significantly reduce the friction factor. The combination drops the absorbed power from over 20 kilowatt to around 6 kilowatt. About a third of the heat to dump. The change also sees the pressure-velocity ratio well within the packing capability. The life of the packing and sleeve in this unit will be dramatically longer. We would estimate, over threefold. Let's take a look back over what we have covered. You are now fully cognizant of flush flow water costs, the significant dilution it creates, and the benefits of keeping slurry out of the packing. On low-pressure applications, if glands are tensioned correctly, the radial force compressing the packing against the sleeve is less significant, so any entrained solids will do less damage, but still reduce wear life. On high-pressure applications, the radial compression force is very significant and high wear rates will definitely occur unless solids are kept out of the packing. It is now possible for you to select what is best for each of your various pumps. Now let's look at the outcome. The summary. For best reliability, keep solids out of the packing. Be careful to adjust the gland follower gently, so packing beds in, as detailed in the installation guide supplied with this training pack. Soft ductile iron, or unhardened shaft sleeves are without doubt the cheapest spare parts, but they will usually result in the highest operating costs. Neither save money. If solids may enter the shaft seal area, or are significant in the flush water, upgrade your packing and use the hardest shaft sleeve you can find, at least 20% harder than the ore solids. Wolfram sleeves usually last 10 times that of the conventional hardened 420 stainless steel sleeves that are standard in most slurry pumps. Instead of stating this standard grade of stainless steel, one manufacturer codes it as C21. By following the recommendations made in this course, most sites will be able to significantly reduce their gland water consumption whilst improving reliability. The more expensive shaft seal components, especially in high-pressure applications, will result in the lowest overall operating costs. Having completed an extensive research and development program on various shaft seal configurations, what is 7D's suggested solution? To reduce flush consumption and average 60%, whilst improving reliability, we suggest combining our gland guard kit, which contains a stainless steel lantern restrictor with a hard Wolfram replaceable tight clearance bush. The bushing is 1300 Vickers hardness, and the material can act as a plain bearing. A specialist slurry-grade urethane lip seal that allows clean flow underneath in normal operation and closes when the flush water is turned off. As the lip seal has water running under it when the shaft is rotating, it has little to no wear. A stainless steel neck ring. Our Wolfram shaft sleeve. This is a 1300 Vickers hardness solid sleeve, well beyond the Brenell hardness scale, about 73 Rockwell C. It is not hard-coated, but rather a homogeneous 1300 Vickers material. A mirror surface finish. 7D's two-fold packing. Our TF1 grade, the most common, has been described in this presentation. Other blends are available. This grade covers both high and low pressure needs and has a broad pH range, thereby allowing rationalization in most plants. A suitably sized Marek valve. Our stocked materials cover even the most corrosive and high-pressure slurry applications. Do we have any other suggestions? Bearing housings designed 60 or more years ago used lip seals, with some attempting to keep solids out via grease purges. If continuously sprayed by water, and/or operating in a dust-laden area, they will be unreliable. In high-pressure duties, gland leakage will water jet, spraying the non-drive end bearing. The older designs do not work reliably in this scenario. Quality brands as KSBGIW, Gould's, and Flowserve adopted bearing isolators decades ago. Many standardized on the well-known Inpro design, which is a market-leading product. Recently, when WW released their new slurry pump design, they also moved to using isolators, dropping their older grease-purged piston ring labyrinth design. Commercially available bearing isolators work well in most industries. Standard commercially available isolators tend to be carbon-filled Teflon, which melts and drops out if mud settles on the rotor, or brass, which is often attacked by mineral processing chemicals, as sodium hydroxide. 7D's Bulwark isolators are specifically designed for mining applications. They are recessed into the end cover, so mud does not settle on the rotor. They are made from a combination of high-grade stainless steels, including a duplex rotor. Extensive tests were conducted in our research and development laboratory, giving us confidence they outlast the commercially available designs. Videos of test work are available. They are stocked in standard kits to suit our safer series, WW, Denver Orion, Svedala, and Metso pumps. We can also supply them for use in other pump brands, gearboxes, electric motors and so on. We hope you have gained knowledge during this session that will enable you to improve gland reliability in any brand of pump. If you have any questions, 7D is happy to help. Likewise, if you have anything to critique, we like to listen. Just press the below Q&A button to send us an email. If you like our cloud training format and would like to add your own sessions, or are another slurry pump enthusiast, your contact via LinkedIn is most welcome. Simply press the following link. We would be hugely appreciative if you could complete our course feedback survey so we can try and improve this and other courses. Thank you for your time.